All right, hey guys, welcome back to another lecture. This is part two of the previous lecture. This is on linear and polynomial regression. Okay, so that's what we're going to do today. So machine learning consists of many different type of learning paradigms known as supervised, unsupervised, semi-supervised, reinforcement. I mean, the list goes on. There are many different kinds, but the most basic kind and the kind that is most machine learning is known for is for supervised. So therefore, that's where we're going to start, and we're going to focus on the idea of supervised learning. The idea of supervised learning is really simple. You essentially have some kind of data, consists of features, bunch of features, and then once you pass the data into some kind of function, it gives you a prediction. In this particular example, this is an actual project I previously worked on. The idea was really simple where we measure pregnant women's blood and urine to measure for various environmental pollutants such as PFAS, lead, microplastic, and then we want to see if we can predict the gestational age, which is when the baby comes out. So normally, if it's below less than 37 weeks, it's called premature, which is not good. Premature. And then if it's below 42 is normal. Therefore, if we can predict premature birth by figuring out when the baby is coming out, so 32 would be too short, 37 will be right on the cusp, 40 will be normal, these will be normal. So if we can predict when the baby is coming, depending on the amount of environmental pollutants they are. So, for example, if you have a lot of pollution, maybe that causes problem with the pregnant woman, and you got some kind of premature birth. So, by basically training a function that allows you to take some kind of data and predict some kind of result is the general idea of supervised learning. Okay, and how do we actually find this function? That is this problem called the regression. We can use regression to essentially find the function. So the goal of regression is really simple. We're trying to essentially minimize a function. And the function is, let's say you have this function that you're trying to find, right? And this is the label you predict. So this right here, if you input X, ideally you want to predict Y. Okay. So you want the output of your function and the actual result to be as small as possible. You can see that your prediction versus the true result, the difference between them can be understood as the error. So you're essentially trying to identify the error, and then you're trying to find a function that minimizes the error for n samples. So if you have n samples, right, you're going to add up all the error square and then divide by n, which essentially is averaging the error square. So you have your error and you want to find the average of it. That's what the meaning of this is. And you're trying to minimize this error. So that's basically the general idea of regression. You're trying to find a function to minimize your prediction error. Okay, so the most common strategy. This is like one of the most common strategy to essentially find the function. The only problem with this formulation is that there are infinite possible functions, right? How do you go about finding a function? That's really difficult. So to find the best function, since it's so complicated to find a function, right? What we normally do is we make some basic assumptions about the function. And these basic assumptions simplifies things. Okay, so one of the assumption we could make, and the most common one we make for the assumption, is that the function, this f, is a combination of bunch of other functions. So So basically, a bunch of functions, you combine them together. We're going to call these bunch of functions, the phi 1, phi 2, phi 3. So that's essentially this equation right here. What it's saying is that we don't know what the function is, but we're going to assume that the function is a combination of phi 1, phi 2, phi 3, all the way to phi m. So so you pick m number of functions, which it's up to you how many functions and what functions you want to pick. But you pick these functions and you assume that your function is some combination of them, right? Depending now, W1, W2, W3, they are just constants. They are just some number. So essentially you can picture W1, W2, W3 as the proportions, right? What certain percentage of phi 1, certain percentage of phi 2 that combines together that give you the best approximation of the function f. So so notice how I specifically tell you that the weights here, we call these weights, W1, W3, are just numbers. Okay, they're just one dimension. And the output of these functions are also one dimension. So these are all one dimension. Okay. So this function here is also a one dimension output. So you put some dimension data d, and then you output a one dimension. And the data is dimension d. The labels are dimension one. Okay. So we call these w, like I said, weights, and they are the kind of give you the proportion of how these functions combine together. Now, these functions, phi 1, phi 2, phi 3, the official name for these are the basis functions. They are the functions we intentionally choose. So we go and think about it, and then we pick a bunch of functions. Okay. And they are called the basis functions. So depending on the basis functions you pick, then we end up with a different algorithm, right? So, like I said, we decide ahead of time. So even before we start our algorithm, we decide ahead of time what these basis function makes sense. Once we decide that, then we essentially find the best weights W to combine the bases together that essentially best approximates the function. So that's a general idea, like that. Functions are difficult to find. Therefore, we make some assumptions. And once we make these assumptions, it gets a little easier. So now that I told you we're going to make the assumption that the function is combination of other functions. Since you could have a lot of functions, this could be a very, very long expression. And by now, you should be used to the idea that long expressions can be simplified by writing them in vector-vector multiplication. So, for example, we can simply split this, right, into a vector times a vector. So we're going to call this vector W1, W2 just W. So W1, W2 are each element, and W is a vector, right, representing the entire vector. Okay, so this right here is W transpose, right? And this right here, instead of phi 1, phi 2, which is each element, is the result of each function, we're going to collect all of them together and call it phi. So notice you want to pay special attention, right? So Wi phi I, Wi phi I, Wi with a subscript. Basically, when there's a subscript, we're talking about individual functions and weights. We're talking about like one of these. But when we talk about W and phi, like right here, we're talking about the collection of weights, like all of them. That's all the weights. And we're talking about collection of all the basis functions. Okay, so you wanna distinguish when there's a subscript and when there isn't a subscript. When they're distinguished meaning. Okay, so it's very important to pay attention to that. And specifically, this vector here, phi of x, has a name. It is called a feature map. So you want to remember that. You're going to use the concept of feature map a lot later. Okay. Okay, so now we can essentially rewrite the minimization problem because now the function we can make the assumption that the function looks something like this, right? So previously we had a minimization problem where we're trying to find a minimum function. And that's the general in the very general regression formulation. However, we simplified this problem. We simplified this problem by making the assumption that the function looks something like this, right? It's a combination of weights plus and functions, combination functions. So now, instead of looking for a function, we're looking for a vector. And this makes life a lot easier because this we did not know how to do. Looking for a vector that minimizes this expression, that we know how to do. So, so finally, there's only one question left. Like, okay, if we know how to solve this, all we need to know is this phi of x. If we know like what this function is, we can essentially plug all the numbers in, perform gradient descent, and solve it, right? So how do we go about picking these basis functions? Well, we're going to learn two types, the two simplest type. There are many, many different types. One is, well, make an educated guess if you can plot them out. Like, for example, this one here, if you plot them out, it kind of looks like a line, right? So you can pick the equation of a line, right? If you pick an equation of a line, you'll look something like this. So in that case, you pick phi 1 equals to x, phi 2, so only 2, that's all you need to create a line. So phi 1 times w1, phi 2, and now phi 1 is just x, right? So it's x. We just plug x here, and phi 2 is equal to 1. And the result is w1 times x plus w2. Now, if you remember back in high school, essentially this is the equation of a line where the the first w tells you the slope and the second one tells you the intercept. So depending on how you pick w1, w2, you're going to get a different line, right? So once you solve this problem, you're going to get the line, right, that give you the least amount of error. If that makes sense. So if we picked basically these basis function with x and 1, then this algorithm is called linear regression because, well, it's a line. So this is linear regression. However, when we use polynomials, so more than a single order, like for example, if you see that the equation kind of looks like a parabola, right? Therefore, well, maybe you can't pick a line anymore. It doesn't matter which line; it's not going to work. So what makes sense is for you to now have three. So phi 1, you pick three basis function. Phi 1 is equal to x2. Phi 2 is equal to x. Phi 3 is equal to 1. Now, if you pick these basis functions, then the equation will end up looking like this. And you will recognize this is the equation of a parabola, right? So this is uh, this will allow, if you find a parabola that makes the least amount of error, then that will be great, right? So if you find a w1, w2, w3 that give you the least amount of error, your parabola should look something like this. Okay. Now, because there are polynomial terms in here, if you use basis functions that look like this is called a polynomial regression. So, like I mentioned previously, um, there are many, many different types of basis functions you can pick, and and depending on what you pick, that's like a different algorithm. So, yeah. So, okay. So, no matter which basis you pick, notice how you can always write the function in this form, where you have the weights, you have the basis, and then you just write it this way, or W transpose phi x. They're the same. So you can always write it this way, and that's very useful. Okay, so now that we know how to pick the functions, And we've only learned two. I mean, there are many, many different kinds, but we're going to stick with these two because they're the easiest. So now that we've learned these two, right? Well, we we previously we previously learned how to solve this one, right? Where it's just x, some kind of vector. Well, this is just some kind of vector, right? There's nothing different between this vector and that vector. It's just that you have to make a conversion first. So let's say you have some data x1, x2, x3. Well, then you need to convert them into phi 1, phi 2, phi 3. Right. So okay. So let's have a more concrete example. Let's say we have three data points, right? X1 is equal to 1, x2 is equal to 2, x3. So these are some data, and given this, we want to predict labels y1, y2, y3, right? Given this, we want some function that when we plug this in, it will predict the label. So that's the general idea. This is original data. Okay, so now that we have the data, we have the label, assuming that we want to go with linear regression, right? Linear regression, which implies that phi 1 is equal to x, phi 2 is equal to 1. Remember, phi 1 equals to x, phi 2, that's what gives us the equation of a line. So let's assume we want to do that. Therefore, remember, this is we if we plug x here, right? We plug x, we just got x back. So if we plug x1 in here and x1 in here, we're going to get x1 here and 1. Right? Let's look at this carefully. If we plug 1 in here and 1 in here, well, this is always going to be 1 and this is going to be 1, right? So therefore you see how we got 1 1. We do this again for the second sample. If we plug 2, right? So if we plug 2 into this equation, it's still going to be 1. Now, if we plug 2 into this one, it's just going to be 2. Therefore, that's how we got 2 1. All right, take a second and see if you understand what I mean. Now, for the third sample, I plug in 3 into the function here, which is just going to be 1. And then I'm going to plug x3, which is 3 here, which will give us 3. So this part here will require you to maybe pause the video to see how high I was able to go from this data into this. Right? This right here is essentially this right here. This first one is equal to phi x1, right? Phi x1. And this one here is phi x2. So now this for each xi is just a vector. This is a vector. That's a vector. That's a vector. So so even though this looks like a function, we can treat this whole thing as just a vector. And when we're minimizing it, right? This right here is the first one. So 1 1. Right? Notice this 1 1. This is the second one, 2 1, right here. And this is a third one, 3 1. So we basically now can solve this as if it was the original problem where it was just use x, because x was a vector. Now this is also vector. All we had to do is do the transformation from x into the feature map. Right? Once we have it in the feature map form, then this could be just treated as a vector. And now we can now solve this problem using gradient descent. All right, so we learned gradient descent specifically for this purpose. Now we have gradient descent, we essentially can solve for W1 and W2, right? We find W1, W2 that minimizes the error. So this is our function. Remember, this is a function. This is what we act. Y1 is what we're trying to predict. Therefore, the difference is the error. We're trying to minimize the error of our prediction. Well, when you divide by n, you're averaging the average error. Okay. So once you found the W that makes your error as small as possible, you can then plug the W into your line. here's your line. You plug W1, W2, and you have an equation, right? Then that's how you essentially figure out the equation to predict the output. So, in summary, this is what you're trying to minimize, right? This is the function that you're trying to identify. This is the label. Therefore, the difference between them is the error square. So the square. So if you add all the errors together from every sample and divide it by n, then that's the average error. So you're you're calculating the average error, and you're trying to find the w. You're trying to find a w that makes the average error as small as possible. Okay, so that's what we're trying to achieve. In linear regression, we would pick where phi 1, and phi 2 as x and 1. In polynomial second order regression, we will pick phi 1, phi 2, phi 3 as these functions. Okay, so depending on which one you want to pick, of course, you can go for higher, x to the third, x to the fourth. It's up to you. But you get the point. So after you've chosen the feature map you want to use, you take your data, and convert it into the feature map, right? So you take your data for every single sample, you convert it into a feature map. So this is for the linear one. So every single sample you convert into that, so that phi x1, phi x2, phi x3, all of them are just vectors with numbers, right? Once you make that conversion, then you can run gradient descent. And when you run gradient descent, the derivative is easy to find. Hopefully, at this point, you remember seeing this as the derivative, right? So you calculate the derivative, and then you update the weights. So the weights with respect to W, right? Weights with respect to W. You start with W now, and then this should be a minus. Should be a minus. Subtract with the derivative, right? With some eta value, which is the step size. That will give you the next one. You do that again and again and again, and that will essentially solve your gradient descent. You will The end result is you will get W1, W2 that is best, that minimizes the error, and you just plug them into the equation for linear or the equation for polynomial, and now you have the function, right? You now have the function. In the future, given some kind of new x input, you can plug in here, and it will give you an output prediction that is as close to its label as possible. Okay. Now, when you're doing this, you can study your error, and you know what? This is the error, right? So if you simply calculate this part, then you have the error right there, right? This is the average. So when you report the error or plot it out, you want to plot this out, and you can see that as you do gradient descent, your error keeps getting smaller and smaller and smaller. Okay. All right. So I want you to know how to plot dots. So I've written the code here. You can plot them out. These are a bunch of points, x points, y points. And then you can create the scatter plot. The scatter are these dots, right? And you can also create the line. So you can draw the line, plot line, right? So this is how you go about plot line. So basically, you can see that we have a bunch of data points. After you run regression, it will give you the line that give you the least amount of error. So you want to be able to visualize this and plot it out. So this is the code that essentially, if you take a quick look, um, make sure you import matplotlib. This is the code you want to study a little bit to be able to do the plots. So, all right. So here is your exercise. There are two exercises. You hopefully, if you can do one of them, that'll be great. Ideally, you can do both of them, but just see if you can do one of them. So the idea is now you have the data set. Here's the data. and here's your label, right? And when you plot them out, they're like right here. Your goal is to basically find the line. You want to find the line that comes like that gives you the least amount of error. The solution should be this. So basically follow through the logic of how we perform regression, minimize it in the code, and then see if you can achieve this. Okay, so this is hopefully like doable. Now, um, if you can do that, a more difficult challenge is a polynomial one. The idea is very similar. So a lot of the code, if you can get this to work, you can just copy a lot of the code here. The only thing that's different is with polynomial, you have x squared as phi 1, right? Phi 2 is x, phi 3 is equal to 1. So you essentially have different bases. Other than that, the gradient descent, the formulation, regression, all that's the same. So if you're really good, you should be able to finish the second one as well. Okay, so that is basically it for today, right? I have written, I I really if you have, I understand some of you don't have the best like programming background, so I did give you guys the link to essentially my version, right? I wrote down how I would do it, how I would do it. In fact, if you're really confused, you can read this, and I recorded a separate video so you are able to essentially like the video is just on my code, just to kind of better explain the code. Um, yeah, that's it. I guess hopefully you can do these exercises and it will be easy. Right? I'll see you in the next class.